Yes.
And it's freezing out there. I forgot to bring my jacket, but I forgot to bring a coat with me.
morning. Okay, on the board is today's attendance question. It's a question about Green's theorem. We have a curve that is formed by the edge of the square. So C is a counterclock. C is a clockwise oriented boundary of the square. Try to draw x is from -1 to +1, y is from -1 to +1. So that forms a square right in the middle of the xy plane. Draw it here. The integral that we are calculating is the line integral. Integrating around the C clockwise, we're integrating x squared x cubed dx plus x plus sin y dy. So that is a line integral. According to Green's theorem, a line integral on a closed curve, closed boundary, can be converted into a double integral within that curve. And this one is nice that the integration region will be a square. So C representing boundary of the square, but if you convert it to a double integral using the Green's theorem, it will be an integration on the square. So it's a square integration region. It shouldn't be too hard to calculate it. So I hope that you still remember what we were talking about with Green's theorem. Now, according to Green's theorem, suppose you do a line integral on a closed curve, so that is closed. Then we have m, which is a multivariable function, m dx. I didn't write mxy because it's shorter. So this is not a number, it's a function. Let's try to remind ourselves, m dx plus n dy, and again, n is a function, not a number. N times n dy. Based on Green's theorem, this is equal to a double integral. Integration. The integration region is a region within this boundary. That's why it's a closed curve, so that the region will be closed up. But this is the part that you have to remember is dn dx minus dn dy, partial derivative. Remember, n and m both representing multivariable function. That's why we have partial derivative instead of derivative. Okay, over here is the a. So this is trying to review the Green's theorem. Based on the Green's theorem, but we do have to remember that the C here has to be counterclockwise. Right? So the question will be, what if it's not counterclockwise? Now, if it's not counterclockwise, then it's clockwise. If it's a clockwise, all you have to do is switch it to a negative, right? If this is a clockwise, it equals this. If it's counterclockwise, then it would equal to negative this. So all we have to do is remember to switch the sign. So in order to switch the sign, what we have here, since C is clockwise, it will equal to a double integral. Instead of dn dx minus dn dy, we can just switch that to dn dy minus dn dx. As far as the double integral. So that's the only thing we have to remember. That's the orientation of the curve, orientation of the boundary. You don't have to remember how to convert it. We need to do the m and n in this case. M equal to x cubed. The n equal to x plus sin y. So converting it to a double integral, it will be double integral of on the square integration region, dn dy. There's no y in m, dn dy. Dn dx. See, that one was a y term, dn dx equal to 1. So really, this is 1 dA on the integration region. So once you summarize it using the Green's theorem, we realize it's just an integration in the integration boundary. So all we have to do is So remember integration 1dA is really the area. And here we're looking at area of a square. So identify what exactly is this area. Area will be our final answer to the question. I hope that kind of makes sense. I hope that you can find the area of the square. Let me turn this down the scanner. If you already have the answer, you can submit it now. I think the final answer should be the area of the square in there. So after we looked at a couple examples already in Green theorem, that Green theorem is a nice way that a lot of times your line integral end up being equal to the area calculation. That also means that the area calculation for some of the irregular things can be converted to line integral. Maybe the line integral is easier than the double integral. So sometimes the double integral is easier, sometimes the line integral is easier. For this question, the double integral is easier. This is a calculation of area of a square. Area of a square equal to the length of the edge squared. And that's why the name is called a square. All you have to do is find out measure of the edge, square that. That's area of square. So that will be this square. This square we have. You can see the edge on this side. It was 1 to -1. And this is -1 on this edge. The top edge is also 1. So the area for the inside of the square is 2 times 2. The 2 by 2 square. That's after I switching it. Okay? If we don't switch it, it would be a -1. That's if it's a counterclockwise. But we did it clockwise. We switched the sign. The orientation made a difference in the question. Question clockwise. So we should be doing dm dy minus dn dx. If it's counterclockwise, we'll be doing dn dx minus dn dy. You have submitted your answer. The area should be the answer should be the area of the square. We follow steps. Step 1, we identify the formula. Step 2, identify the n and n. Step 3, then we switch the orientation. It would be this. And then of course this calculation, this calculation can be this. Right, and then step 4 is finish the calculation. And then step 5, this is the calculation of the area. That can follow the train of thought. I think the answer should be B. You guys get because the orientation is enough. Right in the, we can confirm that if I'm wrong, then we can change it. Last week we were studying string theory. According to Green theorem, this dndx minus dndy. If it's the simple clause piecewise oriented counterclockwise will be dndx minus dndy. However, our question is clockwise, so it should be the opposite. This one we switch it to dndy minus dndy. Or you can follow the original calculation, but add a negative on the outside if it's clockwise. Okay, that's how I know this will be the. Oh, I realized there was a -1, isn't it? Yes, I know you guys were right. You're right. There is a negative right there. dn dx is 1, so dn dx equal to 1, and dm dx E and by, you put a 0, E and Bx equal 1. But there's a subtraction, so it should be -1 calculated. It should be negative in the area. So it's -4. Right, you guys were right. I made a mistake. I didn't do the subtraction properly. So the answer should be -4. See, many of you already have the right answer, but I'm sorry if I was leading you to the wrong direction. The answer should be -4. That's why the whole thing was talking
Oh, wait, hold
about
on.
orientation and stuff. Okay, now, yeah. Okay. We can also confirm this, so we can actually do it one by one as far as the line integral. For example, if you were to calculate one by one, let's see, we don't have to start somewhere. If you start from here, see this one, you integrate the line integral, you will see that the dy, is the derivative line. So you have dx equals 0 on that line, and you're going to calculate here the antiderivative sine y. On here, x equals 1, so it's going to be 1 plus sine y dy integrate on this part. And then the y value is this orientation, the y value is from 1 to -1. Okay, so that's this part. But on this part, you're going to do, you can see that dy 0, because there's no change to the y value. You have dx. So on that part, you're going to have integration x cubed dx, where the x value goes from 1 to -2. That would be the lower limit. This one here, the integrative, is going to be from -1 to 1. And then we also have the x dx equal 0. So that's this part. So this integral will be integration from, try to confirm the idea, integration from -1 to 1. We're integrating a -1. The x sine y is integrating, so it's -1 plus sine y dy. So that's that part. On the last part is here, we integrating is integration from -1 to 1 x cubed dx. Since on this part the dy will be 0, because y is orthogonal, there's no change to the y value. So you can see that what happened is this integral is completely opposite of this integral, so these two combine, the equal to 0 is their opposite value. And over here, if you have sine y dx, sine y, something like that. This integration and this integration limit are opposite. They also cancel each other. So eventually, the only thing that we have is integration from 1 to -1. If you integrate 1 dy, okay, that part going to have a value of -2. This is one integration that's not canceled. On the other parts, we are integrating from -1 to 1, -1 dy. Okay, we're integrating this, you bring -1 to the outside, above the it was also -2. So -2 plus -2 line integral on this part, they give you -2. Line also gave you -2 plus something. That one was cancelled. So when you calculate all four side line integrals, combine them, you have a -2. Even if you follow the range, you would confirm that the double integral provided the same answer to the line. That was the example of the ring theorem. Our answer should be negative. I turned on the scanner. If you haven't already submitted your answer yet, you can submit now. Anyone else that hasn't submitted yet? Thank you. I'm keeping the scanner on because I see some of the answer was incorrect. It was -4. Trying to correct my own mistakes since I was careless with the subtraction there. Zoom out. I did it both with the line integral and the double integral using Green's theorem. According to Green's theorem, it should be the same. You follow the line integral, same answer as we have if we do the double integral using the Green's theorem. Right, do you have any homework question that we should talk about before we start? Any homework question? Okay, if you don't have any homework question, we're gonna continue to chapter 14, section, chapter 14, 14. The title for 14.4 is called surface integral. So it kind of corresponded to 14.2, which we were talking about line integral. So line integral is integration along a line or integration along a curve. Okay, now integration surface integral, it kind of reminds us of a surface area to the, but it's actually corresponds more to the line integral. So surface integral is integration along a surface. So surface integral is actually kind of a two-dimensional integration or a double integral, but it's not the actual double integral that we had before because we're not integrating. You can think of double integral as a integration on the surface represented by xy plane. So you're really integrating on top of the xy plane. But surface integral, you're integrating on that surface, whatever surface that was defined. So surface integral is not double integral, even though the final calculation will be simplified down to a double integral. So calculation of surface integral by double integral, but it's not as simple. All right, to do the surface integral calculation, we'll have to review a formula that we're talking about. That's how we calculate surface area. Surface area is actually a surface integral calculation in itself. It's kind of like a surface integral of 1 along that surface. So suppose the thickness of the surface is 1. Like 1 unit. So we're integrating 1 ds. So you can think of the integration function as a density. In this case, the density equals 1 to surface area, which is kind of like a calculation of mass on that surface. But instead, we're calculating the size of the surface area. So the surface area calculation have this special thing. So it's kind of like a scalar to compare with the actual two-dimensional area. Now you convert the double integral r ds. The ds here is a capital S. It's not the arc length. It's not the arc length parameter we're talking about. The capital S here is a surface area differential. So it's ds. So this is actually two-dimensional differential. It's a special differential. This ds, d capital S equal to this. Equal to root of 1 plus fx partial derivative squared plus partial derivative equal to fy squared. And that was the multiplied by dA, this whole thing equal to ds. That's the surface area calculation. So when you try to calculate surface area, it sounds like area calculation, but this area can have up and down. So it's not flat area. That's why we gotta multiply this thing to capture all the changes, all the upside, up and down in the surface. So the surface actually may be larger than a flat surface. Now, so this is going to be all derivation or formula for ds. In the surface integration, going to need the ds to expand into this formula. So let's see how it's being calculated. Now, if we want to integrate along a surface, it's kind of like when you integrate along a line. When you integrate along the line, you have to have a parametric equation of the line or a parametric equation of the curve. So if we are integrating along a surface, we have to have a parametric form of that surface. That's the next thing we have to focus on. And this is a part that people sometimes get confused, and we may have to practice some of the commonly applied surface. We can't represent all the surface out there, but we try to be able to control or being able to handle some of the common surface. Let's see. seeing that one person hasn't submitted yet. So let's try to name the parametric surface. Right, parametric surface is one defined by three function of two parameter. Right, so we are trying to compare that with parametric equation of a line or parametric equation of the motion of a curve. Parametric equation of a curve has already been talked about and studied in chapter 11. That's the vector value function, where you have only one parameter, that was t. So x equal to xt, y equal to yt, z equal to zt, where t is a parameter. But if we want to use parametric equation to represent the surface is two-dimensional, one parameter is not enough. So parametric surface is using two parameter, three formula, x formula, y formula, z formula. Every formula has two parameters. In this case, it's parametric equation of the surface. X is a bivariate function, y is a bivariate function, z is a bivariate function. In the textbook, we try to use u and v as our parameter instead of t. But we don't have to be restricted by it. Sometimes you can just use z or theta for like cylindrical form of the parametric equation. Which in any case, all we have to remember is to represent a surface using parametric equation, we need two input value. So a parametric surface like having two input value, but three output value. The output would be the x, y, z. The input would be the u and v. Okay. So let's look at example on how do we represent represent a surface with parametric equation. This is our first example. Let me try to go through the steps, and I might have to talk about these slightly differently than the textbook, because textbook hold on to the idea that we have to use u and v. But to me, I think we can use any letter or any notation for the surface. So this is a equation. We are trying to figure out, this is a question. We try to use a parametric representation for a cylindrical surface. Okay, so we have already known how to represent a surface. Start from chapter 10, we realize a three variable equation, a single equation like this already represents surface. So x squared plus y squared equals 4. It is representing a cylinder. With parallel, the cylinder is parallel to the axis because the variable is missing from the equation. So to represent a surface with one equation is already enough. But that doesn't provide your formula for x, your formula for y, and what formula for z. And that's why parametric equation is useful, because it made it possible to do a point-to-point substitution, so you can integrate easily, do a substitution easily. So this is why we prefer parametric form of it. So how we turn that into parametric equation? One thing is this equation presented relation between x value and y value. If we had to write a formula for x and y, and since the x and y simplify follow a circle of radius 2, we can say that x equal to radius is 2, right? 2, it's a curve, it's a circle. 2 times cosine theta. That's easily the representation for the x value. And y is equal to 2 times sine theta, where the theta will be bounded between 0 and 2 pi. It's a full circle. Okay, so that already is representing any point on a cylindrical surface. But then there is one more thing, that is, what about z? Okay, if you only have x and y with one single variable, this fitting this equation, that's a two-dimensional equation with a single variable. It's really a circle. It's one-dimensional, but the surface is supposed to be three-dimensional. So what about the z? Since we don't require any z or z, so the equal to z, right? So then, since we only taking part of this surface, part of the cylindrical surface, that z is between the 0 and 8. So we say z is going to be between 8 and 0. So now we have a equation where it originally it was this equation. Now we have this is our parametric equation, because now you have a formula for x, y, z. And what's our input? You see, the input is theta. This is the input theta, and then this is the input z. So the only input that we have is theta and z. It's a two-variable parametric equation of the surface. That's already the answer. But in our text, we have a preference of using u and v. So how does the textbook handle this question? Convert it to u and v, which goes x equal to 2 cosine u, y equal to 2 sine u, which will guarantee that x squared plus y squared equals 4, right? And then also z equal to v. So that will switch to a complete new set of variables. The benefit of doing this is that the input is u and v. The output is x, y, z. So the benefit is your input is a totally different set of variables than the output and the x, y, z. And this is a slight problem that we have z in the input. We also have z in the output. So some people don't like that. Anyway, let's look at the textbook solution for this question. This is. So we know that the polar coordinate might be a way to look into the relation to x and y, since it does fall on a circle. But on that circle, the radius is 2. So we don't do r cosine theta, r sine theta. We did 2 cosine theta, 2 sine theta. Because the radius is set as radius 2, is set allowed to be 3. And so then you can see that's 2 cosine u, 2 sine u for x and y, and then v is the z value. Okay, so that's the parametric equation that we're provided in the text, and that kind of would be the tone of the whole section. We're trying to convert all the input parameter to be u and v instead of any other variable. But I did try to use the usual variable just so it has a closer connection to what we are learning in the past. All right, let's try one more question. This is again a practice on trying to devise a parametric representation for a surface. So sphere has this equation x squared plus y squared plus z squared equal to a squared, where a is a constant, a is a radius. So this is representing a ball. The surface of the ball only represent the outside, the peel of the apple, if we talk about it. Just the surface, not the inside. So the radius is maintained as a single number. For this, if you try to think of it, since we're looking at surface of a sphere, so spherical coordinate will be the best option if we are trying to devise an equation for x, y, and z. So that's a sphere. So we have x supposed to equal to, if you remember spherical coordinate, x equal to rho sine phi cosine theta, x equal to r cosine theta, r equal to rho sine theta. That's how I remember it, so that it will be have a little bit of connection to what we learned in polar coordinate. So x equal to rho sine phi cosine theta, rho is supposed to be the radius, but radius equal to a, so just to a sine phi cosine theta, and y equal to r sine theta, so the r equal to a sine phi, and then sine theta, and d equal to rho cosine phi, and here we do a cosine phi. Right, this is already enough as far as converting it to a parametric representation. This is already have the formula for x, y, and z individually. The input is phi and theta. And that kind of followed the what we learned in spherical coordinate. But in the text, we did convert it to u and v. Instead of phi, we do u. Instead of theta, we do v. So that's the textbook solution to this question. So recall that the spherical coordinate and we convert it to a sine u cosine v, a sine u sine v, and A cosine U. Those are we replace B by U, replace theta by B, so that it will be consistently using the same notation for the input structure. I mean, you probably would be getting the same idea if you read the text, but just try to go through the idea and then try to illustrate how it can be related to what we did in spherical units. Next question is, what if we don't have any special surface? What if we just have a single equation that goes equal to fxy? How do we convert that to a parametric equation? The answer is actually pretty simple, because if z equal to fxy, then z has already been represented. So simply goes like this. Now, if you got this equation representing a surface, z equal to fxy represent the surface, then we already have the formula for z. So you can simply go like this: x equal to x and y equal to y. And then z equal to this formula that goes fxy. Right, so that will be my first intuitive. X doesn't need a new formula, y doesn't need a new formula, z pretty much equal to fxy. However, there's a little problem to this method, is that we're using the same notation for the input and output. So x is the input, so then the parameter we're using is x and y. And there's two parameters represented. So input xy and output is xy b. So the input and output end up being the same number. In the text, we switch the notation, which we go x equal to u, y equal to b, and then z equal to f u b. So this method, the input parameter is u and b. The output is a coordinate x, y, b. So that's how it's being presented in the text. I guess that's how you would probably prefer. Any question? Okay. Occasionally, I stick to the original variable because it's easier to manage instead of invent and insert new variable. This is a common scenario when we need to devise a parametric equation for the surface. Okay. So now, how do we calculate surface area if we have a parametric equation? Because we already have the surface area formula, it would be here. So that's how we calculate surface area if we have z equal to fxy. Okay. Now, what if we don't have that? We have x equal to x u v, y equal to y u v, z equal to z u v. Then how do we find the surface area? So if we got a parametric equation of the surface, how do we find the surface area? So then we're summarizing into a general form. So the idea is that if you have a single formula for x, formula for y, formula for z, that counts for your whole surface. So the surface is the RUV, or instead of RT, like in chapter 11, now we have RUV. It's a bivariate vector value function. The value of this function is xuv, yuv, zuv, a vector, so a dimensional vector. So in this case, we need to be able to devise the ES. ES is our differential, for the surface area. Just like we have a differential for the arc length, now the differential for the surface area, ES, which is equal to the magnitude of the cross product RU, RB, and then the UDV. So now the UDV is individual differential, which we turn into a rectangular two-dimensional integration, right? So that's the method. That's how we can handle parametric surface area. So here is going to try that method, right? So let's try to calculate the surface of the cone z equal to x squared plus y squared up to the height of 4. So one of the issue in this calculation is that we do not have the parametric surface, right? So we actually have a rectangular surface here. So we could be using the same method that we had in surface area calculation, right? You can find this z, you find the partial derivative of this function with respect to x variable and y variable. It's root of 1 plus fx squared plus fx squared, then dy dx, or dx dy. And we can do a double integral to find surface area. So we already have a formula for this, the rectangular formula for the surface area. Now we're going to apply that to this, just to illustrate the two actually lead to the same answer. So do and follow that. You can see eventually they lead to the same answer, even though since we avoided using the original method, there's an added calculation involved. Let's try to follow what we're talking about. So number one is you have to have a vector value function for this. So let's call that R U V. Okay, I'm trying to write it into a vector form. So x is still x is a u. The y equal to v. What about the z? Z equal to root of u squared plus v squared. If x equal to u, y equal to v, then z equal to this. So that's the vector value function of the surface. That's my surface represented by a parametric equation by a vector. So how do we do this? We are really going to follow that formula. Okay? Let me write down that formula for the surface area. Surface area equal to parametric root of, and here we're going to do magnitude R U. Also, cross product of the two vector RV and its magnitude, and then here we're going to do du dv. Right, we do have to identify that surface there. Okay, so as you can see, if we apply this formula, we have to take care of some things like how do we have to partial factor and how do we have to do the cross product. This is something we've done before. We're applying this formula down right last line there. Just want to make sure that we have that in mind. Keep that in mind. So let's do it slowly, little by little. With math, we handle formula a lot. But when you look at a formula and then not having the ability to analyze the formula and what do we need to do to apply the formula, it's one of the missing skill. So number one, we need to know what's RU. We already have the R. RU is a partial derivative vector. We define the root of this vector with respect to u, the RU. So this one, the first component differentiated with respect to u, we got 1. The second component has no u, so 0. The third one, if you differentiate with respect to u, it's the root, right? The root is 1 over 2 of the root. That's differentiating the root. And then we also have to find the root of inside with respect to u. The root of u squared is 2u. So we have the numerature is 2u. So that's the partial derivative with respect to u. If we want to simplify, we can simplify it to 2 by 2. So that's our u. And we can find a similar calculation. Do a similar calculation, find partial vector with respect to v. There's our vector there. Differentiate this with respect to v. We have 0 and then 1, and then the last one. It's going to be a symmetry, right? U and V has a symmetrical position there. So you're going to find very similar reasoning. The root of this one with respect to V would be root of U squared plus V squared. There's a 2 here, but it's going to cancel the total in the inverse V. So it's V over U squared plus V squared. So there's a partial derivative vector. And the next thing is we got to find is cross product. You see, we do it slowly by slow, a little by little to derive the whole calculation. And here we're going to do the cross product. We do RU cross RV. The reason I put this vector in vector form because it's easier to look through the matrix. The first component will be it's right? So it's negative u over roots of u squared plus v squared. The second component, I guess, I move that over 1 and 0. Most multiply and subtract. So we have negative v over roots of u squared plus v squared. The last component is here. So I'll subtract 1. Okay. So that's the cross product. But we're not integrating this. We're integrating the magnitude of the cross product. So if we take the magnitude of r u cross r v, suppose we v, okay, that would be square root of square the first component, then you have u squared over u squared plus v squared. And we square the second component, you can get v squared over u squared plus v squared. When you square negative numbers, the negative number quantity is squared into. Last one, we have a 1 square, so this whole thing equal to, we see common denominator, the denominator is u squared plus v squared, so it's u plus v squared over u squared plus v squared. So it's actually 1, 1 plus 1 is 2, so this is really 2. Okay. So obviously we're gonna be getting this, it's gonna be a double integral root 2 du dv. So it's interesting to say that we have the root part is a constant number. You bring the root 2 outside, it's a simple area calculation. Okay, so now will be that means we are calculating a double integral du dv. It's an area calculation, right? So area calculation, hopefully it's not a hard area. In here, it's up to a height of 4. By height of 4, we mean the 4 of the cone, right? The 4, that means this equal to 4. Right? If this equal to 4, that means r equal to 4 is a circle with radius 4. So the area of a circle with radius 4 is pi r squared, but r equal to 4, so 16 pi times 16 pi is the area, and then we multiply 16 pi times 2 is the final answer to the question. That's my derivation of the whole thing. We can zoom out to see. Hope I didn't make it actually complicated. The main part is try to calculate the magnitude of the cross product. And once that part is simplified down to a single number, and the rest is analyzing the integration region. And the integration region is bounded by the boundary of the surface. So boundary of the surface, you got a cone that extends indefinitely up high. The height is what's posing as a boundary. Now, that was my solution. In the textbook, you can find the solution. It was in the vector form using the ijk as a component, as the vector form. I did the component form vector. This is a vector form of the vector. So it's still the magnitude of the cross product in the being 2. So it's really a 2 time area calculation that you see in the last line. Any question? This was an example illustrating how we apply this formula. And let's look at one more example. This is the one that we did not try, and it represents a really interesting surface. A surface is a what people call helicoid spiral bend. I wonder how normally we in real life we have ramp that goes high. For example, in those design of the parking building, or in regular building, we have those spiral stairs. So they're not the spiral stairs may not be a continuous, but it's a step function of the plotted. So anyway, the function goes u cosine v plus u sine v. Then the angle is the v, and then v also represent the height of the surface. Okay, so obviously we have to put it in boundary for both of the u. The u is from 0 to 1. So if it's a spiral curve, then u is constant. Like if the radius is 4, u 4, if the radius is 2, u 2. That's a spiral. It's some spiral is something that we learned already in chapter 11, but now we don't let a u to be a constant. We make u between the assertion now using u is between 0 and 1. So then this is representing a surface instead of a curve. Now we're trying to determine how what's the size of the surface area and calculation. C. And it's our second example calculating surface area. You can see many things that we did in chapter 10 or 11 that's coming back to us, like representing spiral motion, also the surface area calculus, surface integral represented using the magnitude of the cross product. So if you are a little bit rusty on cross product calculation, now it's in practice. So that's the one that we want to calculate. Again, my habit, I mean, everybody have a different way of handling things. The R is being represented by a vector. Instead of arguing, I just write R. It was make it to make it fact surfaces. The first component is u cosine v. The second component is u sine v. And the last component is v. So that's u. Okay, so then we can calculate R u. To right. Partial derivative vector. So R u. So we differentiate it with respect to the u variable. So differentiating u, derivative u equals 1, so we have cosine v as a coefficient. Now, second component differentiate with respect to u is also 1. It's 1 times sine of v. Right, and the last component has no u, so derivative 0. So that's the partial derivative vector. Now we also find the derivative r with respect to the v. So R v, and you can also think of this as R dr dv. It would also be a vector because R itself is a vector, so it's derivative, the partial derivative of vector is a vector. So we differentiate this first function with respect to the v. Derivative cosine v is negative sine v, so it's negative u sine v. So that's the first component. Second component is derivative sine v, which is cosine v, and then cosine v. That's this derivative. The last component derivative v 1. So those are the partial derivative. Okay. Try to match them well so then we can find the cross product. So next, let's try to find the cross product. So we would do R U cross R V equal to. The first component is this 2, and you can see it's sine v. Sine v times 1, and then u cosine v times 0 equal. Second component, we move the cosine v and negative u sine v over. So to make it easy for the cross multiply subtract. So then the answer is negative cosine v. That's the second component. The last component is cos 2. These 2. So we have u cosine squared v minus negative u sine squared v. That's u cosine squared plus u sine squared, which essentially so that's the That's the cross product of these two vector. And then we will find the magnitude of the two as as required by the integration of the surface areas. The RU cross RV magnitude. It's magnitude of this vector. So the magnitude calculation is root of every square. So this will be sine square v plus cosine square v, which equal 1, and then plus u squared. So that's the calculation. And then moving on back to the actual calculation set, determine the surface area, still surface area calculation. So the surface area is equal to a double integral, and you're going to integrate 1 plus u squared, and then we do du dv. We need to determine the boundary for u and v, which we were given. Okay. U is from 0 to 1. And then V is from 0 to 4. I realize this integration only have U in there. And then the dV would be an independent integration. So 0 to 4 pi dV is 4 pi. So the calculation 4 pi times 0 to 1 root of 1 plus U squared. I wonder if you have fast way for doing this integration. This definite integral is kind of a classical example where if you want to calculate, you need to tangent theta. So we will do a substitution method that u equal to tangent theta. So then the 1 plus u squared is 1 plus tangent theta squared, which would equal to secant squared theta. So then the root of 1 plus u squared actual equal to secant of theta. On the other hand, because u equal to tangent theta, du is equal to root of the tangent, root of the tangent equal to secant squared theta. A lot of review of trigonometry. So that's the conversion. So we converted to a integration of the root part becomes secant. The du becomes the squared. So it's really integration of secant cube theta. Now applying the formula in trigonometry, this is equal to secant theta times tangent theta plus logarithm. I will spend extra time explaining how to integrate secant cube. But that's another, the method is integration by part, but now save time, let me give you the formula for secant cube, plus tangent theta. So that's the integration for secant cube. And then we want to bring that back to the original variable. Secant theta is this root. Tangent theta is this u. So this part is really just u times squared. And then plus natural log. Here we have secant theta, which is so the tangent theta is u, and then the secant theta is root of u squared. That's our antiderivative, and now we're going to plug in u. The original equation u is from 0 to 1. Plug in 0, plug in 1, finish the calculation. We'll be able to achieve that integration value. Back to the text solution. It's over here. You can see. Oh, I see it right now. Like something was missing. There's 1, 2. I hope I didn't mislead you there. This is a integration of secant cube. Let me give you a more formal formula for it. It's a very popular example that we did in calculus 1 for integration, integration of secant cube. There. So that was that's not what I prefer. Right, it was integration by parts. This formula is equivalent. There's for every single integration question, there are multiple solutions for it. But definitely do not prefer the internet giving me that answer, right? This integration, that was the antiderivative of secant cube. Sorry, I felt like there's a common formula that you can find anywhere, but it's in our text. If you want to refer back to it, the method is, I think you saw it there. And the method is doing a integration by parts, which would look like this: integration of secant cube theta. You bring out a secant square theta. It's like this integration of secant theta, the tangent theta. And you can make u equal to secant theta, b equal to tangent theta. We can do integration by part. So if you do integration by part, it will equal to secant theta, tangent theta, plus integration of tangent theta, the secant theta. The integration by part. And then right here, if we derive this one, we're going to see secant cube again. So it's one of those algebraic methods that causes us to eventually give us 1/2 because there's secant here, there's secant there. And we add both side equation, and then the final step involves the division. It's a tricky method that we calculate calculus. Right, I really made this longer because I delve into other things unrelated to what we are doing here. But I do feel like reviewing the integration by part and reviewing the trigonometry integral will help as far as smooth out the calculation, lower the calculation difficulty. So will definitely be helpful if we try to review those concepts. Right, this calculation solution that was the integration of 1 plus u squared. It has an antiderivative. The proof of this formula is to letting u equal to tangent theta and doing the substitution. Do a quick substitution integration. That's this example. Sorry if I made a messy presentation, but that's what's behind the scene. The textbook solution is kind of brave, so explains the related topic. All right, let's actually work on the surface integral. So far, what we were talking about, it's all surface. It is all surface area calculation. So what is exactly surface integral? It's when you have a surface represented by like here RUV represented by a parametric equation where the parameter is u and v. It's on the so-called UV line. RUV has x component, y component, and u component. So if you're integrating along this surface, then all formula has to be affected by representation. For example, if you're integrating function f, x, y, dz on this surface, in that case, the f, x, y, z, the x, y, z in the input for the function f will follow the same representation. So x becomes the x in v, y becomes the y in v, z becomes the z in v. So that has to be substituted into the function f. So it's different from the past. When we were doing triple integral or double integral in last lecture, we don't have to change our integration function. We change our integration limit or integration variable. We don't change a lot of time. We don't change our integration function. But with surface integral and electrical, we have to change our integration function according to the corresponding integration region. So in this case, the x, y, z are changed, and you also have to multiply the ds. We have to multiply the magnitude of RU plus RV. So that definitely gonna change the function that we're about to calculate. So let's look at a question. Let's say we want to calculate the surface integral of the function x times y times z over the part of the cylinder x squared plus y squared equal 1 about the first quadrant in the XY plane, between equal 0 and equal 2. So as you were looking at the function, we have a cylinder. So if you are calculating a surface, really the title says surface integral. So we're integrating function along the surface. Then the number one things we have to do is being able to derive or write down the surface parametric equation of the surface. If we can't now start doing that, then we probably don't have the right function to integrate. So then let's start. Okay. So since it is a surface integral, so at least we have to have the surface indicate surface clear. The surface is a cylinder, so integrating on is a cylinder. All right. We have wave kind of cylinders such as x equal to r cosine theta. The r equal to 1 in this case, so it's really cosine theta. The y equal to sine theta. And then here, in the first quadrant, that means the theta will become between 0 and pi over 2. The first quadrant, and then between the equal 0 and the equal 2, last one is the z, where z is between 0 and 2. This is how we represent the surface there. And so now, how do we already derived one of the formula before. Let's try to follow the textbook, turn that to U of V. So we will have x equal to cosine u, y equal to sine u, and then z equal to v. So we have a U of V. So in this case, u is angle that is between 0 and pi over 2. And then v is a v value, which is between 0 and 3. These are going to be our integration limit for the surface integral. So that the boundary is already there. Let's look at how we calculate. We're supposed to integrate this, right? To integrate surfaces. So that integration theoretically is this double integral. And then we're going to integrate x, y, z. Because it's a surface integral, we're doing ds. Right, so that's the original notation. We're doing it according to this new variable, because we're trying to follow the formula of the surface. So it becomes like this, double integral. The x is cosine u, so we cosine u. The y is sine u, so x, y, z become cosine u times sine u, and then times z, z will be v. So this is our derivation of the x, y, z. It becomes like all three of that. And the next thing is the ds. We know how to calculate ds now, and then that found me a little bit annoying because you have to have the extra ru false rv magnitude, and then du dv. I remember u is from 0 to pi over 2, and then the v is from 0 to 2. That'll be the calculation. So we still have to derive exactly what is that cross product. I still feel like the easiest thing to handle cross product is write out the vector. So we have r itself is equal to this vector that goes cosine u, sine u, and then v. We find the partial derivative with respect to u, which is equal to negative sine u. Find the derivative 1 by 1. I felt like we've done this before. Yes, the example. RV right, this one has no V. So 0, 0, 1. Now the cross product is RU cross RV, which is equal to the vector cosine U. And then we have negative sine U. 0. So sine U here. The last component is cross product between these two. It's actually 0 there. So then we can find the magnitude of, obviously the magnitude of this would be root of cosine square plus sine square, which is really 1. So that says this whole magnitude. It's nice that it's equal to 1, so it doesn't add extra computation difficulty. So there we have it. And then finally, we will finish the surface integral calculation from here. Right, the integration will be integrating 0 to 2 O squared dv. Right, we have a v dv separate variable, and then there's integration 0 to pi over 2 sine u cosine u. Sine u cosine u du, right? And then the antiderivative of v dv is v squared over 2, integrated at 0 and 2. Evaluate at 2 is 2. So this part is equal to 2. Now for the trigonometry, it's sine u cosine u, derivative sine equal to cosine. So this is really d sine. So sine u d sine u. The antiderivative is sine squared u over 2 with power rule. And then you can see the derivative of sine squared u over 2 is going to be 2 sine u cosine u divided by 2, right? So that would be the derivative. So we find the right hand derivative, evaluate at 0 and power 2. At 0 is 0, and power 2 equal 1. So it's supposed to equal 1/2. We multiply the 2 and end up having an answer that equals 1. Interesting. So this is all the calculation we've done so far. The textbook did have the cross product calculation in a different version. Feel free to try it, whichever works the most effective way to find the cross product. Just find the way that you can have a higher rate of success. Then you follow whatever works best for you. That's one example for surface area calculation. There's a way of converting from the surface area differential ds to the du dv to the regular double integral. So that's something that sometimes it takes time to look into. This is this example. See, there's a reason where the surface integral is necessary. One of the reasons is to calculate flux. Let's say we have a vector field, the capital F, M, and P. So this is a 3-dimensional vector. It's different from the 2-dimensional vector that we mentioned in the Green theorem. This is a 3-dimensional vector. Now, so you kind of have a surface, and then we have a 3-dimensional vector that will interact with the surface. We can find something called the flux of F across the surface. Okay, across the surface defined by the vector R that we are talking about, R which has x, u, v, y, v, v, u, v. So the flux is defined by F dot NES. The N here is a unit normal vector of the surface. I don't know if you still remember how to determine normal vector of a surface. The normal vector of the surface is really the derivative vector, the gradient of the surface. Normal vector. The normal vector is a vector we need to determine the tangent plane of the surface to find partial derivative in x, partial derivative in y, and partial derivative in b. And those are those are going to be the direction vector of your plane. Okay, so we still need to know the normal vector. But here's a unit normal vector. So you're going to turn that normal vector into a unit vector. That's an N. Okay, so realize there are interesting thing about it here, because dx has root of x fx squared plus f squared plus 1, but then the n has that root in the denominator. So maybe the n factor multiplied by ds will cancel the fact that we have to handle the root of fx squared plus fy squared plus 1. So that's why we actually have a easier way to calculate the flux. That is essentially a dot product between the unit, between the normal vector of your plane and the vector in the surface. What I mean is this. So we literally try to understand the idea of the dot product is literally a dot product calculation that we did here. Alright, so let's try to look at it from a vector perspective. What we have is f. If we try to write the f shorter, f is this vector represented by m and p, the vector, right? And then we can identify the normal vector of a surface. If you remember, if your surface is v equal to f x y, right, what was the normal vector that we applied? Which will be this fx negative fx. We can turn that into this right, and the minus. We can actually make it either one, minus fxy equal to 0, right? So then you can see the right side of this equation. You're going to find the derivative with respect to x is negative fx, and then negative fy, and then 1. So that will be for this surface, the normal vector for the surface, you will find the left side of this equation, find this gradient vector. That will be the gradient vector. So if you calculate the dot product between this vector dot this vector, you'll find this vector. So essentially this f dot n is the direction of the vector field dot product the direction of the perpendicular direction of your surface. And if these two are along the same surface, and you have higher flux, if these two are perpendicular to each other, maybe you will have a smaller value of the flux. It's calculation flux across surface. So this is something that we may have to calculate in physics or engineer. And that's why we practice calculation here. So let's look at an example of how this calculated and realize this definition made it possible for us not have to worry about the cross product R cross RU cross RV. So sometimes if you're calculating a flux or vector field across a surface, this surface integral do not require that cross product. We've converted into this calculation of rectangular integral there. So what we did is dx dy. There's no need to convert it back to there's no need to convert it back to the UV vector of your surface in that sense. All right, let's look at an example. Just if we got time. So let me not to focus on too much on calculation. So here is the example. We have a vector field that's really the position vector. Three-dimensional position vector of the vector is x dot y z. X is the first component, y is the second. So this is an outward vector going out. And then we have this surface is a conical surface. So it's the surface of a cone. Z equal to root of x squared plus y squared is 45 degree cone. And then the x squared plus y squared less than 4 is within a radius to a circle. So a cone is now infinitely large. It's like on the top of the cone is have a radius 2. We're going to calculate the flux of f across this surface, and that's a calculation. Let's see. So what we're going to do is identify the surface. Find out the component of the vector, which is x, y, z, and then find out the component of the surface, the gradient vector of our surface, which will be x over x squared plus y squared. negative x over root of x squared plus y squared, and negative y over root of x squared plus y squared. The last component should be 1. So that's a component. So you're gonna take the f vector dot the gradient vector of your surface. That's exactly what we're doing here. Yes. And now we're integrating, and the final answer ends up being 0 for the dot product. And I think we're out of time. That's it for today. We probably will work on more detail if you have any question, feel free to mention that. I assigned the homework, try the homework question. We're probably gonna practice tomorrow. That's it for today. Thank you. For the attendance question, you're still haven't finished yet, but let me get your answer to the question. If you have wrong selection, feel free to make it. And we'll one more student. Okay.